Welcome back to our easy-to-follow Conditional Gaussian Simulation course. Prepare for Lesson 2, where we are going to explore Simple Kriging, covering data exploration, variography analysis, and interpolation. The best part, we are using our scripts to automate the entire process with QGIS. Think of the possibilities. Create your scripts once and use them across many projects without ever needing to write more code. But that's not all. We are going to introduce new scripts to reverse Gaussian anamorphosis data transformation, effortlessly returning your values to their original scale. Ready to boost your geostatistical analysis skills and unlock the full potential of Simple Kriging? Stay tuned, press play, and let's get started. Today we are going to be working with the Meuse River dataset. This dataset is related to contaminated soils. Then let's go to load the dataset in QGIS. We are going to load a CSV file. Then we have to select the option delimited test. Then select this option. Is this spreadsheet as a CSV file? Open. Make sure you have selected this option. Then make sure you have selected point coordinates. For the X field has to be the X coordinate. For the Y field has to be the Y coordinate, as you can see in our table. And for the reference coordinate systems, here you have the code is 28992. Then add. This coordinate reference systems is good. Okay. And close. Now we can also add the satellite imagery from Google Earth. If you want to get a full explanation about the Meuse River dataset and also how to get this dataset, my recommendation is to go to the GeoRGV community website at giscourse.online, go to the first geostatistics course that is totally for free, get enrolled in this course, and then you are going to be ready to learn. Then press continuous learning, and in the second lesson here, you are going to get that data set, okay? And also from the website, you can download the CSV file. But also you have the option to watch that lesson through the YouTube channel. Is this lesson over here? Here is the full lesson, but when you are using YouTube, you don't have the option to download the file, right? If you want to download that spreadsheet, you have to do that one through the website. Now, before starting with the exploratory data analysis, I would like to make a very short introduction about Simple Kriging. Many people, maybe they are wondering why to explain Simple Kriging as a part of the Conditional Gaussian Simulation course. And this one is one of the main reasons. Because Simple Kriging is a less complex technique that can serve as a starting point before addressing more advanced methods like ordinary Kriging, universal Kriging, and of course, conditional Gaussian simulation. But let's go to see a very short introduction about Simple Kriging. Simple Kriging is a geostatistical interpolation method that estimates values at unsampled locations using spatial variability information. It considers the spatial correlation structure among data points and relies on variogram theory. This technique assumes a constant mean for the variable of interest throughout the study area. Simple Kriging provides accurate and reliable spatial estimations. Let's consider the simplest case, where we have 3 sample locations and 1 unsampled location, and we want to estimate the value at the unsampled location. In order to calculate the estimation at the unsampled location x sub 0, we can use this mathematical expression, where we are using the values at the sample locations multiplied by the weight between the unsampled location and the sample location. And this one is just a summation of a linear combination between a sample location and the weight between the unsampled location and the sample location. Then what type of information we have to solve this equation? We know the values at the sample locations. We know all these values, but we don't know the weights. But also what we have is the distance between the sample locations, and also we have the distance between the sample location and the unsampled location. Then with the information of the distance and the information of the covariance function or the semivariance function, this is the spatial correlation structure of the data, we can make the construction of a matrix in order to calculate the weights, because it's the only thing that we don't know in this equation. Then to calculate the weights for a simple Kriging, we have a system matrix of two matrices. The first one is an inverse one, as you can see here, and the second one is a regular one. And what we have to do is multiply both of them. The first one is related with the sample locations. Is the distance between the sample locations. Could be the covariance or could be the semivariance. It depends if we are using the covariance function or if we are using the semivariance function. And the second matrix is related between the sample locations and the unsampled locations. Then let's go to see how we can calculate the covariance. For example, for the first value. The first value is the covariance between x sub 1 and x sub 1. As this one is the same, the value here is going to be 0. It means that for all this diagonal, all the values are going to be 0. For the second value is going to be the covariance between x sub 1 and x sub 2. Then it's going to be this pair of samples, x sub 1 and x sub 2. Then we have to calculate what is the distance between these 2 points and then project that distance on the x-axis here, because this one is for the lag distance. Then when we have the lag distance between these 2 pair of samples, we have to go up until we get the covariance function. When we reach the covariance function, we have to project the value on the y-axis. Then here we are going to have the value for the covariance. Then with this value of the covariance, we can place here at the matrix. And then we are going to do the same for x sub 1 to x sub 3. And that one is going to be the third value for this matrix. If we are using the semivariance, the function of the semivariance is going to be the same. Then the only thing we have to calculate is the distance between x sub 1 and x sub 2. Then go here, project that value on the x-axis, then go up. When we reach the semi-variogram function, then we can project this value on the y-axis, and then we are going to have the semivariance according to that lag distance. Then we can place that value in this matrix. And for this matrix, it is the same, but in this case, is the distance between the unsampled location to the sample locations. And then when we have all this distance calculated, we can plot over here and see what is the semivariance or the covariance according to the matrix that we want to use. In this example is the covariance. Once we have all the values placed in the matrix, we can calculate this system and then we can obtain the weights. Once we have the weights, we have to just multiply the weights by the according sample location and then make the summation of all of them. At the end, we are going to get the estimated value at the unsampled location x sub 0. Remember that in Simple Kriging, we are assuming that we have a constant mean at the entire study area. And because of that, the matrix system is the simplest one. If we are using, for example, ordinary Kriging, the matrix system is going to be a little bit more complex. Another important thing is when we are using conditional Gaussian simulation, one of the first steps is to calculate the weights according to this function also. Later, in the conditional Gaussian simulation, we are going to use a random vector in order to provide the random values for calculating the certainty of the phenomenon, right? That's a different thing. But at the beginning, the first step is going to be the same as a simple Kriging. It indicates how important it is to understand this process, right, inside of the conditional Gaussian simulation. Now, let's go to start with the exploratory data analysis. First, let's start with the analysis of the data distribution. And we are going to use the script number 6 that it was created at the lesson number 5 of the first geostatistics course. Remember that you can watch that lesson through the YouTube channel. Is this lesson number 5, but also you can get that lesson at the GeoRGB community website, and is this lesson number 5 over here. You can download also the scripts here. Is this file. Then let's go to run. I'm going to run the version number 2 because I did some modifications, and now I'm going to show you that modifications. Then here we have to add the layer. In this case is the muse data. Then the parameter that we are going to analyze is the zinc concentration. As you can see in this attribute table, we have several parameters, but we are going to be working just with the X and Y coordinates and with the zinc concentration. Here for the zinc concentration, we have a minimum value of 113 and a maximum value of 1839. These values are part per millions, ppm. Then I'm going to add all the labels, but I'm going to pass the video faster. Then for the label X, we have the zinc concentration in ppm. For the label Y, we have the number of samples. The title of the graph is going to be the histogram. The subtitle of the graph is going to be raw data because we didn't apply any modification yet. Then the X minimum is for the zinc concentration, as we said, is 113, and the maximum value is 1839. And the number of bins for the histogram is going to be 12 bins. 12 bins is because when we are doing the root square of the total number of samples, in this case the total number of samples is 155. As you can see over here, 155. If we are doing the root square of that value, 155, you are going to see that is 12.4, okay? And that's the reason because I decided to put 12 bins. Then now we can run this script and double click to open. Now we can make the screen bigger. This table is a new modification I added to the script. You have to understand that the scripts are like a living entity that change over time. Then at the beginning, I created the basic script that it was just the histogram. But now I decided to add this table because I believe it's pretty interesting to have in the same graph the information related with the mean, median, standard deviation, minimum value, and maximum value. At the end, it depends on each person. You can build the scripts according to your necessities. And from my point of view, it was interesting to have this information on the graph, and I decided to add it. This histogram is showing the zinc concentration in ppm at the x-axis and the number of samples at the y-axis. For each bin at the top, we have the total number of samples. And as you can see, in this case, most of the samples are located at the left part of the graph, indicating that the histogram has a big skewness to the left. Also, as we can see on the table, the mean value and the median, they are pretty separated. This asymmetry on the histogram is indicating that the mean value is not representative of all the data set. And when it happens, the semi-variogram that we are going to get is not going to be good. And if the semi-variogram is not good, the model that we fit on the semi-variogram to have the spatial structure of our data is not going to be good. Then if the model is not good, the estimations that we are going to get with the Kriging are going to be no good. Then when we are dealing with Kriging, it is very important that the data is follow a normal distribution or close to the normality. Then as close the data is to the normality, better are going to be the results. It doesn't require that we need to have a data that exactly follows a normal distribution. We can do Kriging estimations with data that it is not following a normal distribution, but we are going to get the best results as closer is to the normal distribution. That is the point. Now let's go to move on to the next script that is going to be very useful to identify outliers on the data distribution. That script is the number 13. I'm going to close this one, and it's going to be this one, the box plot, together with the histogram. And this script was created at the lesson number 6, is this video over here, of the first geostatistics course. Also, you can get the file with the scripts to be integrated in QGIS at the GeoRGV community website at gscourse.online. Here you have the file to be downloaded with this script. In this script, we have to add the same information as we did for the other one. The layer is going to be the layer with the data set. The parameter is going to be the scene concentration. And now I'm going to add all the labels. Well, I already added all the information and the script is ready to be run. Double click to open. Let's go to make the screen bigger. This histogram is the same as this one. However, in this one, we added the box plot. The box plot is pretty interesting to see the distribution of the data. What we can see with the red line is the mean value and the black line is the median. And we can see that the red line is far away from the majority of the samples. And the reason of that is because we have here a big high values related with the scene concentration that push the mean value to this area of the graph. And all these values, all these high values, they are outliers. Also, what we can see is that the box is situated to the left because of the skewness. At the end, we cannot use this data set to do Kriging interpolation because the results that we are going to get on the semi-variogram are not going to be good. Then we have to look for a solution. We can, for example, try to remove the outliers and see if the data distribution improves and is more close to the normality. However, to remove the outliers, the high values related with the scene concentration, we have to justify that one. And the question is, can we remove it, these values over here? And the answer in this case is not. These values are very important of the data set. And they are not something related with errors with the instrumentation or part of other process different than this one. There is no justification in this case to remove the outliers. Then the next step that we can think is to transform the data. We can transform this data to have a normal distribution. The transform the data is the second option, right? The ideal scenario is to work with data without any transformation. Then if we cannot do that one, the next step is to try to transform the data. Then after transforming the data, check if we have a normal distribution or close to the normality. And if it happens, then we can use that transformation to do the Kriging estimation. And there are different types of transformation. For example, the logarithmic one, the root square, the inverse. And all these transformations, what they are doing is squeezing or expanding the data. but we are keeping the original variable. But what happens if any of this kind of transformation doesn't work? We make the transformation and we can see that the data is not still following a normal distribution or something that is close to the normal distribution. And we are going to see that we are going to have problems with the semi-variogram. Then we have to look for a more aggressive way to transform the data. And then is when we can use Gaussian anamorphosis. Also, for conditional Gaussian simulation, we don't have any other option than having a perfect normal distribution. Then for conditional Gaussian simulation, we always have to force the data to have a perfect normal distribution. Then Gaussian anamorphosis is an ideal technique to transform the data when working with conditional Gaussian simulation or when working with data sets that we want to apply Kriging estimation, and it is now possible to have a normal distribution or close to normal distribution using the simplest transformation techniques. Remember that when we are using Gaussian anamorphosis, as we explained at the previous lesson of the Conditional Gaussian Simulation course, the first lesson that it was related to Gaussian anamorphosis, this lesson over here, we said that when we are doing Gaussian anamorphosis, we change totally the variable. Then we are no longer have the original variable because we transform that variable in a new variable. And this variable is totally different. That's one of the inconveniences of using Gaussian anamorphosis. But also it has its own advantages because we can get a perfect normal distribution when the data set is pretty complicated and we cannot reach that one with a different type of transformations, and also when working with conditional Gaussian simulation. Then now what we are going to do in this example is to apply the Gaussian anamorphosis to do the simple Kriging. And if you want to use the script that I'm going to use now, you can download that one on the GeoRGV community website. All the theory related to Gaussian anamorphosis was already explained in this lesson. Then if you want to get more information, I recommend to watch that lesson. You can do that one through the website, or also you can watch that lesson on the YouTube channel. But be aware that here you are going to have some restrictions. Then we can go to QGIS. And now we are going to apply the Gaussian anamorphosis. Then go to the simulation and it's going to be this script. Step 1, transform data, Gaussian anamorphosis. Double click, select the layer, the parameter that we want to transform. In this case is the zinc concentration. We have to add the X and Y coordinates here. The label X is going to be the zinc concentration in ppm. And the title of the graph is going to be the Gaussian anamorphosis. Then we are going to add the minimum and the maximum value for the zinc concentration. The number of polynomials, we are going to add the same as we did at the previous lesson. And the number of means is going to be 12. I already added all the information and now I'm going to run the script. Double click to open. Now we can make this screen bigger. What we can see here is the original data. What we can see here is the transformed data. We have a perfect normal distribution with a mean of 0, median of 0, standard deviation of 1, and a pretty symmetric histogram, where the minimum value is minus 2.8 and the maximum is 2.76. I have to mention that for the Muse River dataset, for the zinc concentration, we can also use a logarithmic transformation, and that type of transformation here is going to work well. And we are going to have a data distribution that is going to be close to the normality. However, in this lesson, the goal is to use Gaussian anamorphosis because that's the data transformation that we are going to use for the Conditional Gaussian Simulation course. Then the goal in this lesson is to see how we can apply Gaussian anamorphosis with Simple Kriging and how we can revert this transformation after applying the Kriging interpolation, because that is going to be the second most important part of this lesson for today. How to go back to the original scale of the scene concentration. This script has been designed not only to provide the graphs, but also to provide an spreadsheet with the X, Y coordinates plus the original data associated with the scene concentration and the values for the Gaussian anamorphosis transformation. And that's what I'm going to show you now. However, when I run the script, I forgot it to add here to save the spreadsheet. And now what we have is this temporal file here, right? We can open the attribute table, and we are going to see that for this data transformation, we have the X and Y coordinates, we have the original values for the scene concentration, and we have the Gaussian anamorphosis transformation values. And also, if we added here, well, I closed already the windows, but if we added the link to save the file, we are going to get this spreadsheet. This spreadsheet is the one we get the other day when we run the Gaussian anamorphosis with 43 polynomials. And this information that we can see here in this spreadsheet is the same information that we have here at the attribute table. Then what I'm going to do now is cut this file, copy, and I'm going to paste here in the folder for the datasets. Paste in the Simple Kriging folder. And this one is the file I'm going to open now with QGIS to do the variography analysis. Then we can close this one and let's go to add that file. Then it's going to be a delimited test. It's going to be this one, open. Make sure you have selected this option, this one is good, coordinates are good. Then we can add, close. And as you can see, is this data set over here. Now we are going to use the omnidirectional semi-variogram cloud. And to do that one, we are going to use this script over here, number 1. Remember that this script was created at the lesson number 2 of the 3rd geostatistics course. Then if you go here, number 2 is this lesson over here. Then if you want to get this script, just get enrolled in the course, go to exercise, and here you can download the scripts. And that's what we are going to do now. Then we have to select now this data set, because it's the one with the transformed data. The parameter that we are going to use is the Gaussian anamorphosis transformation. The cutoff is, in this case, is going to be the total extension of the area. The longest one. In this case, what we are going to select is this extension from here to here. As you can see, is 4,710 meters approximately. Then we can add 5,000 meters, for example. Then here, 5,000 meters. The X label is going to be the lag distance in meters. The Y label is going to be the semi-variance for the scene concentration. But remember that in this case is the Gaussian anamorphosis transformation. The title of the graph is going to be semi-variogram cloud for the scene concentration. And the subtitle, we are going to add Gaussian anamorphosis transformation. To just, if someone sees the graph, they are going to be aware that it's about a data transformation and what type of data transformation. Then I'm going to add the labels, and let's go to run the script. I added already all the labels. I want to specify that we are going to create the semi-variogram cloud of the omnidirectional one, because we are not going to specify any direction for the cloud. It's going to be the omnidirectional one. And here I added for the subtitle Gaussian anamorphosis transformation. Then we can run this script and double click to open. Now we can make this screen bigger. I always like to to do the omnidirectional semi-variogram cloud in all the extension, because this graph can give us a lot of information. What I'm looking for here in this graph is if there is any pattern or any kind of trend on the data. That is pretty important, because if we have a trend, then we are not covering the assumption of stationarity. And if we are not covering the assumption of stationarity, we can apply Kriging interpolation. Then if it happens, we have to remove the trend, and then we can do the Kriging interpolation. But in this case, we cannot see any trend, and that's good, and it is indicative that we have stationarity on the data. Also, this graph is very interesting to identify if there is any cluster, and also if there is any outlier value. And in this graph, it looks pretty normal, pretty good, and I believe we don't have any of those things. Now, the next step is to see what is the structure of the variability on the data set. Then to do that one, we are going to use the script number 10. Let me put this one over here. Number 10 is this script over here. That is about of the omnidirectional experimental semi-variogram. Remember that this script was created at the lesson number 4 of the third geostatistics course. Is this lesson over here, and if you want to get that script, you can download from here. Then we can run that script. It's going to be this layer. The parameter is going to be this one. The cutoff, we are going to add the same as before. But yes, we added here 5,000, but when we plot the graph, it is showing just 4,500 meters because there is no more information from that distance. The longest one is 4,500 meters. That's the reason, because we cannot see here 5,000. But that's okay. We can add even 5,000, and the adjustment is automatic. Then 5,000 here. 5,000. Lag distance in this case is not really important, because now what we are going to have is a general view of all the structure, right? Because we are going to add all the extension. And what we want is to have enough points to be representative of all the data set, right? Then, for example, 500 for the lag distance is going to be good. The label for the X is going to be the same. The label for the Y is going to be the same. The title of the graph, we are going to copy, and now we are going to modify this one a little bit, because it's going to be omnidirectional experimental semi-variogram for the zinc concentration, and we can remove the cloud. And for the title is going to be the same. And we are not going to save, but if you want to save the graph, you can do that one also. Now we can run this script. Let me move over here and run. As you can see, when we run this script, we have this information. This information is related with the number of lags that we have. In this case, we have 9 lags in total. And for each lag, we have the total number of pair of samples for each lag. Also, we have the gamma, that is the semi-variance. I mean, we have first the distance. The distance is in meters for each lag. And also we have the gamma, that is the semi-variance for each lag. Then we have another parameters that is related with the direction and the vertical direction, the horizontal direction and vertical direction for the semi-variogram. But in this case, as we are using the omnidirectional one, there is no values over here. It's 0 and 0. Then we can double click here to open the graph. And let's go to make this screen bigger. Important things that we can see in this graph is the pair of samples. The pair of samples, as you can see, is quite big. it is indicative that we have a very robust semi-variogram because we have a lot of pair of samples for each lag. Also, important thing that we can see is that the data has a structure because the semi-variogram is growing up until here, then reach this point, and then start to go down. In this case, we can see that the correlated area of the graph is until here, with this range approximately, where we can reach the seal and then goes down. And that's very important, again, because it is showing that the data has stationarity. And if the data has stationarity, we are covering that assumption for the Kriging, and we can apply Kriging. For example, if we have a semi-variogram that is showing a growth that is exponential, it will be indicative that we have not stationarity on the data. Now that we can see that there is nothing weird on the general view of the omnidirectional experimental semi-variogram, we can be focused on the area where there is a spatial correlation. That is the around from 0 to around 1,300 meters until here, more or less. Then we are going to make a zoom on this area of the graph. Then we can use the same script, but we are going to change the parameters. Then it's going to be this script, but now instead to use a cutoff of all the extension, we are going to add here, for example, 1,500 meters. And we can add a lag of, for example, 75 meters. We want enough lags in order to fit the model properly. If we have at least 10 lags, we have 10 points where we can fit the model, and that's important. Then with these variables, we can now run this script and check how it looks like. Again, as before, now we have 20 different lags, and for each lag we have the pair of samples, we have the distance, and we have also the value for the semi-variance. Now we can do double click to open the graph and make the screen bigger. Now we can see better the structure. We can see that even we can put a cutoff shorter, because as you can see, it goes until here, and over here it starts to go down. Then, for example, 1,250 for the cutoff is going to be enough, because we don't want the model to be fitted in those lags over here, because the lags that we have in this graph are the lags that are going to be used to fit the model. And with that model, we are going to do the estimation of the Kriging. Then we don't want to use lags where there is no data that is not spatially correlated. Then I'm going to make a modification here, and I'm going to select a cutoff of 250. And also, I believe we have even too much lags. Then what I'm going to do is to put a cutoff of 1,250 meters and also a lag of 100 meters. That's the modifications I'm going to do for this one. Then go here, as I say here, 1,250, I mean 1,250, and the lags every 100 meters. And I'm going to run this script again. Double click to open, and let's go to make the screen bigger. And this one looks better for me. It is more clear. We have also a strong semi-variogram because we have a lot of pair of samples for each lag. And we can see the structure pretty clear here. We can see that we don't have even nugget effect, or if we have a nugget effect, this one is going to be very small. We know that the range, I mean the seal is going to be over here approximately, and the range over here. Now that we have the semi-variogram that we want, we are going to fit a model on this data. And to do that one, we are going to use the script number 19, this one. And this one also has a small modification that I'm going to show you now with respect to the original one. Remember that this script was created at the lesson number 5 of the third geostatistics course. And if you want to get this script, you can download over here. Is this script over here? Then we can add here the information. We are going to use this data set, this variable, cutoff, as we said, is 250. Lag distance is 100 meters. Seal, we can add the values that we get here approximately. Okay, we said that the seal is going to be over here, and we are assuming that we don't have too much nugget effect. Then it's going to be around 1.5. These values that we are adding over here, they are just approximations. But we have to add these values in order to initiate the computational process. The model is going to be the spherical one. Has to be right like that, exactly. In other way, it's not going to work. The range, we say that it's approximately 1,250. The nugget maybe is 0.1, something like that, or even less. And now I'm going to add the labels, but I'm going to pass the video faster. At the end, I added for the X label, lag distance in meters, for the Y label, semi-variance. The title of the graph is going to be a spherical model thing, and for the subtitle is going to be Gaussian anamorphosis transformation. And I'm not going to save the graph. Then run. And in these pop-up windows, we can see that the model is also print. We have a nugget effect that is 0.1. We have the spherical model. We have that the partial seal is 1.29, and we have that the range is 1176 meters, 0.1. Then we can double click to open the graph and make this screen bigger. And that's the modification I added to this graph. I decided to add a table with the value of the nugget, with the value of the partial seal, and with the value of the range, and also with the model that we are using. As you can see, the model fits really well on the lag points. And that's a very good signal that we are going to get a good model, right? Then it is important to indicate here that this semi-variogram has been created with the transform values using the Gaussian anamorphosis. And remember that when we are using Gaussian anamorphosis, we are not using the original data because we create a new variable. And this model is fitted in that new variable. But this variable is not the original variable, it's the variable that we created. It's going to be more precise and more realistic to fit the model on the original data, that on data that it comes from a variable that we created from a new variable. And that's something that we have to consider when we are using the Gaussian anamorphosis. Because as I said, we have an order of priorities, right? The first priority is to avoid any type of transformation. Then if we cannot do that one and we have to transform the data, use a simple transformation. And if we cannot do that one, then we are going to use a more aggressive transformation. And that's things that you have to think when you are transforming the data. And this one is a good example because here we are feeding the model on a data that is not coming from the real variable. It's coming from a variable that we created. Now that we have the model, we are ready to use Simple Kriging to estimate the values at the unsampled locations. But first, we have to work on the grid that we are going to use for the interpolation. The first thing that we have to do before to creating the grid is to see what is the minimum distance between two pairs of samples. To do that one, we are going to use the matrix distance script. that it comes by default on QGIS is distance matrix. Double click. Now we are going to select any of these two. We can work with these two layers, but I'm going to use this one. Then I'm going to use the transform parameter. Then I'm going to select the same layer here and the same parameter here. And I'm going to run this script. Now we can close these windows and double click here to open the distance matrix. I mean, we want to open the attribute table. Now here, if we click here at the distance, we are going to get that the minimum distance between two pairs of samples is 43.93 and the maximum distance is 4,440 meters. Then I'm interested in the minimum distance because the minimum distance is going to provide me the minimum pixel resolution that I want for my grid. And in this case, it's going to be 40 by 40. Because if we make something smaller, we are going to have a higher computational cost to process the geospatial analysis. And if we have, for example, 100 by 100, we are going to be losing some information. Then the pixel resolution has to be at least the minimum distance between two pairs of samples. And in this case, the pixel resolution that I am going to use is going to be 40 by 40. Now that we know what is going to be the pixel resolution, we can close this one and we can remove the distance matrix here, remove this layer. And the next thing that we are going to create is a shapefile with a representation of the pixel resolution. It's not going to be the grid that we are going to use to do the Kriging interpolation. Is just a visual representation of the pixel. That shapefile is going to be very useful if we want to improve the representation of the pixel graphically speaking, okay? Then to do that one, first we are going to load a layer with the perimeter of the area of study. I have this perimeter here in a shapefile. Then I have to go here, Simple Kriging, shapefiles, and here I have the perimeter. Open, add, and close. This one can be created pretty easily. Just go here, layer, create a new layer, new shapefile layer. Then here put a name, save the file, select the geometry. In this case, it's going to be polygon. Select the proper coordinate systems and OK. And then you can edit this layer. I'm going to modify some things here because I want this layer to be transparent. Then I have to select this option, transparent, and the line is going to be 0.3, and we can put this one in a red color, for example. Apply and OK. And here we have the perimeter. We are going to use this perimeter to define the limits of the grid. Then go to vector, here research tools, and create a grid. In this case, the grid is going to be a rectangle. The grid extend, we are going to use the perimeter. The horizontal spacing is going to be 40 meters. That's the dimension of the pixel that we want. The vertical spacing is going to be 40 meters again. And the rest of the parameters are okay. The reference coordinate systems is also good. Now we can run this one. Close, and this one is a provisional file. And this file, now we are going to carry it with the perimeter to have the shape that we want for the grid. Then go to vector, geoprocessing tools, clip, and we want the grid to be carried with the perimeter. And also we can save this layer. Save file. And we are going to save in the Simple Kriging folder in the shape files. And this one is going to be grid, the 40 by 40. Save, and now we can run this one. Oh, I did something wrong here. Remove. I believe I didn't select the shapefile. Okay, then let's go to run this one again, but let me remove this one here. Then go vector again, geoprocessing tools, clip. This one is good. This one is perimeter. Here is going to be safe. But here you have to make sure that you select a shapefile. This one here. Then it's going to be grid 40 by 40. Save and run. Close. Now we can remove this one. Remove. The next step is to create the real grid that we are going to use for the interpolation. To do that one, we are going to use a script that is called as a regular points. Double click to open. Then here the input extent is going to be the perimeter. The point spacing is going to be 40 meters. And we want an initial inset from the corner left high side that is going to be 20 meters. In this way, we are going to center the point at the middle of each square. Then 20. The reference coordinate system is good, and now we can run this script. Close. Now we are going to cut these new regular points with the shape of the perimeter as we did before. Then go here, geoprocessing tools, clip, regular points, and we want to overlay the perimeter, and we can run this one also. Close, and we can remove the regular points. Okay. Now if we make zoom, we are going to see that we have one point at the middle of each square. That is going to be the unsampled locations, right? We are going to make the estimation of the zinc concentration for each of these points. And the raster that we are going to get is going to have this pixel resolution. This one, this shapefile, the grid 40 by 40, is going to be the representation of our pixel resolution. Then the next step is to add here the coordinates to these points, because as when we open the attribute table, we can see that this layer with the clip, the points, just has the ID, a column for the ID. In total, in this case, we are going to estimate 3,153 points. Then to add the coordinates, we are going to open the edition. Then we are going to go to the raster calculator here, open field calculator. And here we are going to put the name X for the X coordinate. Here is going to be decimal number. This parameter is good and this one is good. And we are looking for the X coordinate. To do that one, we are going to use the dollar symbol and then press X. And as you can see, it's this one over here. It returns the X coordinate. Then double click and OK. And now we're going to do the same for the Y. Then open the field calculator. This one is going to be the Y coordinate. This one is going to be decimal number. The length and the precisions are good. Here the symbol of the dollar, Y, and we are going to select this parameter and OK. And now we have the X and Y coordinates for each of these points. Now we can close the edition, save. And the last thing that we need to do with this layer, the one with the points, with this layer, is to change the geometry. In this case, this layer, the geometry is a multi-part, and we have to convert this one a single part. To do that one, we are going to use a script that it comes by default in QGIS that is called multi-parts to single parts. I did something wrong. Multi-part to single parts. Double click to open, then select the layer, is this one, and we are going to save the file. Then save to the file, and first we are going to save this one as a shapefile, and we are going to call this one as a shapefile grid points. Save. And run this script. Now we can close this one, and also we can remove this layer. Now we have the grid points as a shapefile, but what we need is to convert this one to CSV file. Then we click here, export, save feature as, and here we have to select the CSV file. Then let's go to save this file in the proper folder, Simple Kriging, in dataset, and I'm going to select the name grid points. Make sure you have selected this option. Save. The coordinate reference systems is good, and all the other things are good, and OK. And now if we go here, Simple Kriging, datasets, we have the grid points in a spreadsheet. We can open this one. OK. Open copy. And we have the spreadsheet with all the points with an ID, the X and Y coordinates. This file is going to be our grid. That's the information that we are going to use to create the raster with the Kriging estimations. Then close, go again to QGIS. And now the next step is to create the Simple Kriging. Then let's go to see the script that we are going to use. Then create a new script. And I'm going to paste here what I did already. I'm going to save this script with this name. Then I'm going to cut this one here. And I'm going to remove these two spaces. Paste the name here and save. Now let's go to see what kind of information we have in this script. All these things is going to be the interface for the pop-up windows. This one is the packages that we are using. This one is the models that I added to the script. We can use the exponential, the spherical, the Gaussian, and the matter. Here we have a code to add the grid with the CSV file. Then here is to convert this grid as a spatial feature. Then with this one, we add the coordinate reference systems to the grid. Here we have a code to define the variable. This line is to create the variogram. This one is to fit the model on the variogram. And this one is to do the Kriging interpolation. It is important to indicate here that we have the variable beta. With the variable beta, what we are saying is that we are going to use the Simple Kriging. If we don't have this variable over here, it's going to be ordinary Kriging. But as we define this variable, it's going to be applied the Simple Kriging. And in this case, beta is equal to 0 because that's the mean value that we have in our data set. Remember that we did here, let me see where we have that one. Here, the mean value is 0 for the data transformation. And that's the value that we are adding at the beta parameter. Here we have two different options. The first option is using all the samples that are located in the range. But for the second one, we can specify a maximum number of samples that we want to use to do the Kriging interpolation. Then, for example, if we have a range that we have 1,000 of samples inside that range, maybe we want to reduce the number of samples to do the interpolation in order to reduce the computational time. Then the next two lines is to export the maps as a raster. Then with the next line, what we are going to do is extract the interpolation values from the Kriging. And then with the last one, we are going to add these values to a spreadsheet. And then in this script, we are going to create the raster maps, but also we are going to get a spreadsheet where we are going to have the X and Y coordinates plus the interpolation values for each of our grid points. Then we can close here and run the script. Let's go to R, simulation, and now we have here a step 2 simple Kriging. Then double click to open this script, and now we can add the information. The layer that we are going to use is a step 1. Because in the step 1 we have the Gaussian anamorphosis transformation. The parameter is going to be this one. The cutoff is 1,250. The lag distance is 100 meters. It is very important to put here the same values that we put previously to define our semi-variogram. It was this semi-variogram here, right? And this one is for the model. But for the model, the values doesn't have to be exactly, because the fit is going to be automatic based on this semi-variogram. Then the nugget, it's approximately 0.1. The model has to be exactly, is the spherical. The range could be approximately, I'm going to put 1,200, and the partial seal also is approximately. Remember that we have to add these values to initiate the computational process. Then here, the grid location, where we save the grid points, okay? This one, remember, that has to be a CSV file. Then go to the Simple Kriging folder, datasets, and that's the grid points that we created as a CSV file. That's the one we want to use for our interpolation. Then local Kriging, we are not going to use local Kriging, then we don't have to define any number of samples that we want to use, because we are going to use all the samples inside the range. Then here we can save the variance map. Also, we can save the prediction maps. We are going to save that ones, okay? Save, file. I have a raster folder here, and I'm going to put here map variance, and that's for the Gaussian anamorphosis transformation. Save, and also I'm going to save the prediction. This one is going to be map prediction for Gaussian anamorphosis transformation. Save. And also what I want to save is the spreadsheet, okay? Then here, save. This one is a CSV file. Then I'm going to save that one in the dataset. And it's going to be a step 2 because it's the Simple Kriging. Save. And now we can run this script. Then, as you can see here in the pop-up windows, it is saying using Simple Kriging. And also we have print the model. And this model has the same values as we have over here. And also you can see that, for example, here the range is 1176, but when we put the values here, for the range we put 1200. But as I said previously, the script fits the model automatically. And then these values doesn't have to be exactly, it can be approximately. But the values that has to be exactly is the values that define the semi-variogram, the cutoff and the lag distance. Then we have to add here the values that we calculated previously when we was doing the variography analysis. Also, now we can close this one here. Also, what we have here, as I said, we have an spreadsheet. We can open this spreadsheet that has been loaded here in QGIS. And as I said, we have the X and Y coordinates and the estimation value for all the grid points, for the 3,153 points, okay? These points are these points here, the ones that we created, right? It's these points here. But we don't have the information in these points. If we open the attribute table here we have just the X and Y coordinates, because that new information is in this spreadsheet. This spreadsheet has been saved in the folder. Here at the dataset, we have a step 2. In step 2, we have that grid, open as a copy, where we have the X, Y, and also the estimation for the unsampled locations. That is the 3,153 points for the grid. Also, what we get with that script is the maps. First, we have the variance map. The variance map is the error. Then we can edit this map, properties, select here single band pseudo color, select here, for example, equal intervals, 10 classes, and it's going to be, for example, the ramp. We can select the plasma one, then apply, and OK. Then what this map is saying, that as closer we are to the samples, smaller is going to be the error of the prediction. As you can see, here we have 0.1 and here we have 0.8. In these areas where we don't have any samples is where we are going to have the maximum error on the prediction. If we put here the data points on the map, you are going to see that where we are having the samples is where we have the lowest variance for the error. Then the second map is the prediction map. Is this map over here, and also we can edit this layer. Properties, single band pseudo color, equal intervals, 10 classes also, and the ramp is going to be the same. The plasma one, apply, and OK. And this one is the prediction map. And with this raster file, we can see the pixels, right? But if you want to see even better the pixels, we can use the layer that we created. This one, we can put here, this one on the top, here. Then we can edit this layer, properties, make this one transparent, make this line even not that thick, 0.1 for example, apply, and OK. And as you can see now, you can even see the pixels better with this layer, but that's up to you. You know, that's something optional. If you don't want to use it, you can take it. But if you want to use it to have a better representation of the pixels, you can add it and you can edit this shapefile according to your necessities. The next step is to convert this raster to the original scale. As you can see, now we have this scale. This scale is associated with the Gaussian anamorphosis transformation that we did. And now we want to have here the values associated with the zinc concentration in ppm. We want to have the same scale as we have over here with these values, right? Then we are going to use the next script. The next script is going to be the step 3, and is where we are going to revert to the original scale, all the grid points. The first thing that I'm going to do is to load the new spreadsheet that we created. Then go to the limited test, and it's going to be the step 2. Open. Make sure you have selected this one, point coordinates, x with x, y with y, the reference coordinate system is good, and then we can add this one. Close. And remember that each of these points, what they have is the x and y coordinates plus the simple Kriging prediction. When I was designing the scripts for the Gaussian anamorphosis to be integrated in QGIS, I was thinking what could be the best workflow to do all the geostatistical analysis. And at the end, I thought that the best way is doing all this analysis step by step. And that's the reason, because at the end, I decided to use 4 different steps. We already saw the first and the second one, and now we are going to see the third one, and later we are going to apply the fourth one. Then the first step is the Gaussian anamorphosis transformation of the original data. Then the second step is to apply the Simple Kriging or the Conditional Gaussian Simulation with the transformed data. The third step is to revert the estimation values from the Simple Kriging or the simulation values from the Conditional Gaussian Simulation to the original scale. And the fourth step is to create a new raster with the back transformation. Then with these 4 steps, we complete all the process of the simulation or estimation using Kriging or using Conditional Gaussian Simulation. And the interesting thing about this way with steps is that we can see for each step what's going on. For example, for the Gaussian anamorphosis transformation, that is the first step, we can change the number of polynomials, then we can see the graph. Then, for example, for the second step, we can see the maps, we can see the results that we get on the estimation or on the simulation that we are going to do in the third lesson. Then for the third step, we are going to see what is the results that we get when we go back to the original scale. And in the fourth step, we are going to see the final map with the results after going back to the original scale. Then if there is anything wrong between these steps, we are going to identify that one earlier. And that's pretty good, because sometimes I was thinking maybe it's better to do one script that process all the things together, but even that script is going to be very complicated and looks like we are missing information at the middle. But if we are doing the things step by step, we can see what things we are doing for each step. And then looks like we are not missing any information, and we have more information to take better decisions. Because in every step, we document everything we do with spreadsheets, graphs, and maps. Now let's go to move on to the third step. I'm going to close this window here, and I'm going to press here, create new R script, and I'm going to paste what I did already. Paste. We are going to save this new script with this name, step 3, back transformation Gaussian anamorphosis. Cut, I'm going to remove these 2 lines, and I'm going to save this one here. Paste and save. Then what we have in this script, we have the interface for the pop-up windows, we have the package that we are going to use, and then here, all these ones are related to the Gaussian anamorphosis again. Then we are going to use the original data to do the Gaussian anamorphosis model. Then the second one, all this one, is to go back to the original scale. what happened here? Okay, here we have the model for the Gaussian anamorphosis. And here, what we are going to add is the new spreadsheet that we have with the values of the estimation or the values of the simulation from the Simple Kriging or from the Conditional Gaussian Simulation. Now we have those values that it comes from the raster that we created. Then we are going to extract those values and we are going to use this model to go back to the original scale. That's how it works. And at the end, we are going to create a new spreadsheet with the new values. That values are going to be all the values in the grid, but in the original scale. Then with these values here, now we can create a new raster with the original scale. And that's the goal. Then we can close this one here. Now we can go to R again, simulation, and we are going to run the script number 3. Then first, what we have to add the original layer. The original layer is the muse data. Then the parameter original is going to be the zinc concentration. The x coordinates has to be the x coordinate and the y coordinate has to be the y coordinate. The number of polynomials, the same as we added at the beginning. In this case is 43. Then the second layer that we have to add here is the step 2. The step 2 is this grid points over here. Then here we have to add what is the variable, in this case is this one, what is the x coordinate, what is the y coordinate, and now also we can save here the spreadsheet. And this spreadsheet is going to be the step 3. Then we can save here the step 3. Then save, and now we can run this script. And now as you can see, here is added a new attribute table that we can open. And now we have the values in the original scale. Also, we have here the spreadsheet that is the number 3. This one here with the values in the original scale. Open as a copy. And now we are going to use this new spreadsheet to create a new raster with the original scale. Then let's go to close this one. Let's go to QGIS. We can close this one also. And we can close this one also. Then let's go to create a new script. I'm going to paste what I did. I'm going to save this first step like final raster original scale. Cut this one. Paste over here. Save. Remove these 2 lines. Save. And this script, that one is for the interface. That one is for adding the new spreadsheet. This one, we can remove this one. We can remove, in fact, this line, because this one, if we want to remove the first column. But in this case, open. As you can see, the first column is the x coordinate. When I designed the script, I have an ID in this column and I decided to remove it, right? But in this case, we don't need it because it is the x coordinate and we need that one. Then here, we have to remove this one here. Then remove, save. This one is to provide spatial coordinates to the grid. And this one is to create the raster. Then we can close this one. We can go to QGIS, go to R, simulation, and open a step 4. Now here we can add that spreadsheet, that is the number 3. Okay. And we can save also the raster in the raster folder. That is going to be the map prediction. And I can put here original. Then we can save and run. Close, and now we can edit this map. This one doesn't have the coordinates, looks like. We can add it, the code is 28992. This one here, okay. And now we can edit this layer. Go to properties. And here, equal intervals, 10 classes, as we did before, and we are going to use the same scale. That is the plasma one. Apply and OK. Now, again, if we want to have a better representation of the pixels, we can take this layer from here and put this one on the top. I want to take this one out. And now we can see the pixel better, right? And also we can add on the top the original data set. And this one is the final result for the Simple Kriging. And now if we check the values, they are in the original scale. As you can see here, sorry, you have to select the original map, this one. And now we can click on the pixels. And as you can see, this value over here is the concentration in ppm. For example, here we have 1209. Here we have 195 ppm, 684, and etc. Now let me save the project. We are going to save as a Simple Kriging. Going to put here lesson 2. Save, and also we can do the cross-validation to see how good is the Simple Kriging model that we created. Then let me see, we have the script here. Structural analysis. We have the list one now cross-validation for the correlationalization model is not this one. And we have this one also. The leave one out cross-validation, omnidirectional graph. We can use this script. But we have to do some additions in order to work with Simple Kriging. Let me edit this script. And the thing that we have to modify is here. Then we have to add here the beta parameter that is going to be equal to 0. That is indicating to the script that we want to use Simple Kriging. Then we can save this one with the same name. This one, no, it's 41. But I cannot see what is 41 over here. But we are going to add Simple Kriging. Then save, close. Now go to R again, structural analysis. Then here we have to use the step 1, that is the spreadsheet that has the transform values for the Gaussian anamorphosis. Then it's going to be this one, and we are going to introduce here the same parameters as before. Cutoff is 1250. Like distance is 100 meters. Partial seal, remember that these values can be approximately. Spherical model, range, again it's approximately. Nugget, it's approximately. And number of beams for the histogram is going to be 12. And title of the graph, in this case, is going to be leave one out cross validation for Simple Kriging. And then we can run this one. And here we have the model and also some statistic parameters. The one interesting for us is the root mean square error, that is 0.5. Also, this script creates a series of graphs That helps a lot to have a better understanding about the model that we created. Remember that this script was created at the lesson number 8 of the third geostatistics course. Is this lesson over here: cross-validation, leave one out cross-validation, and key fault cross-validation. Then in this lesson, you have all the theory about the cross-validation, all the explanations. And also here you have the file to download the scripts. In this lesson, you have a step-by-step how you make the representation of these graphs. That is the same graphs that we can see over here. Then as a general thing, I can say that what we want here is to have a low values compared with the original values that we have. In this case, the range that we have is this one, from minus 2.8 to 2.76. But here, the maximum value that we have is 2.10, and the minimum is minus 1.8. It is indicating that these values are a little bit high compared with the original range that we have. Also, here what we want to see is that all the pink points are on the line, indicating that the data is following a normal distribution, the residual values. Also, the histogram, we want to have a normal distribution. We want all the values to be closer to 0. In this case, as you can see, most of the values are close to 0. However, we have just a few residual values that are over here and also are over here, that they are a little bit out of the main data set. These values can also be reflected over here and also here at the tail. And these high values are also the ones that we can see here as a big circles. In the last graph, we have a scatter plot about the predicted values against the observed values. And what we want is all the blue dots to be as closer as possible to the red line. The red line is going to be the ideal scenario, where we have the same values for the predicted and the observed. And in this case, the difference is going to be 0. And if the difference is 0, then we are going to have a perfect model. In this case, we make a regression line for the blue dots, and it's the black line. As farther the black line is to the red line, worse is going to be the model. Then this kind of graph is interesting to be used to compare with another model. Then in this case, what we can do is to do also the cross-validation, but in this case, for the ordinary Kriging. How we can do that one? Then we can use this one, because this script has not the Vera parameter. Then we can add here the same information as we added over here. Then here we have to add the step 1. This parameter over here, the cutoff is going to be the same. Sorry. The lag distance is going to be 100 meters. CL is going to be here. Before I added 0.1. That's not really good approximation. 1.3. But it is okay because the model is fit automatically and we need to adjust approximately values, right? Then the nugget effect, this one is 0.1. Number of beans 12. The title is going to be the same, but in this case we are going to add ordinary Kriging. Control C, Control V here, and this one is going to be ordinary. Then we can run this one. Now we can compare the models. Here we have this model, and here we have this model. The models are identical. There are no differences. And here for the root mean square error, we have 0.5418, and we have here 0.5413. The difference is very small. And now we can also open the graph over here. Double click to open and make the screen bigger. Now we can compare both of them. Let me make the same dimensions. This is for Simple Kriging, and this is for ordinary Kriging. We can see some differences here for the maximum and minimum value. As you can see, 0.89, 1.817, 1.814. But the QQ plot is almost the same. The histogram also, they are pretty similar. And also for the scatter plot, they are pretty similar. Then in these two models, we cannot see any differences. They are more or less the same one. Well, that's the end of this video tutorial. I know that the exploratory data analysis and the variography analysis was something very, very short. We didn't go very deep in that concepts, but just to let you know that the goal of this video tutorial, it was just working with Gaussian anamorphosis, right? How to do the transformation, how to revert the transformation to the original scale. If you want to have more knowledge on structural analysis, data exploration, my recommendation is just to take time to watch the previous tutorials. Even here at the 4th geostatistics course, you have some lessons related to how to perform ordinary Kriging, how to perform universal Kriging, regression Kriging, Kriging with external drift, and also co-Kriging. There are a lot of information in these courses, you know. Even for the 3rd course, I believe it's 10 hours of content related to the structural analysis. Then the things that you can do for the variography analysis, right, and the data exploration, there are too many things. But we have to do just a few things in order to avoid to make a very long video. And that's what I did for this lesson. Thank you very much for watching this video, and see you on the next lesson.